We'll now go into 8a.2.3. We are going to take the roots of a complex number. So if z is the complex number, then this expression z exponentiating by 1 over n, and n is an integer, this is taking the nth root of z. Okay, and we can also take the negative n root, or z to the power negative 1 over n, the reciprocal. So we'll see what we're trying to do here. But maybe as a first start, let's try to take this number, and then isn't this the square root of z? And let's have a very simple expression for z is equals to nothing but 4 plus j0. So this is square root of 4 plus j0, and this is square root of 4. And then we have the answer plus and minus 2. So you realize that taking square root will give us two values if we are interested in the entire range of the real number. So we can have positive values as well as negative values, because minus 2 of times square is equals to 4. So we now maybe begin to appreciate later on why the roots are multi-valued over here. Okay, let's begin. The idea of taking the nth root, we again make use of De Moivre's theorem by extending it to find the nth root. Okay, so let's retain our expression for z in the polar form, complex exponential form, Rej theta, and we want to take the kth root, okay, or the nth root. Okay, so the nth root is basically saying take z and then find the values of w1, okay, actually it's w0, w1, w2 until wn minus 1. You'll realize that there are n solutions for this root by the fundamental theorem of algebra. If the expression have is to the power of n, then there's n root. So how do we take this? Again, we put the value of z in the polar coordinate of the complex exponential form here, and we're exponentiating by 1 over n. You will see that actually it looks very much like the De Moivre's theorem. The 1 over n is shift into the individual term over here, as well as here. So the modulus is exponentiating by 1 over n for the root, and the angle is actually theta divided by n. But then you realize that, hey, we want to have k equals to 0, 2, and minus 1 to get all the nth root. Okay, and now if you do not like it in complex exponential form, some books will show it to you in the polar form. So this becomes here, there's no change, and this of course is by Euler's identity. Ej theta becomes cosine theta plus j sine theta, and because this in expression is being used, so this expression and this expression remains. Now k goes from 0 to n minus 1. So this is how we use De Moivre's theorem to find the nth root. Okay, but in the next few slides, we'll show you some proof. Alright, I again took this from this video link called Andrew McCarthy. He explains it very well, and now I would show it to you and explain it as well. Right, first we have z in this form, Rej theta, and Ej theta is in the rectangular form. That's it. And we say that the De Moivre's theorem, when we're going to find the nth root, basically again all we are doing is that we are taking theta plus 2k pi divided by n for cosine, and same theta plus 2k pi divided by n, and then k goes from 0 to n minus 1. Alright, this is the fractional powers of De Moivre's theorem. So the question is, if we have z equals to this value, what is the nth root of z? The first idea is that, hey, this guy need to satisfy z to the power 1n exponentiating by n. So what we are saying is that these guys will cancel and we'll get back z. So we want this to satisfy so that, hey, at least we get back what we want from the root. So if z is nth root, then this is the nth root. When we exponentiating by n, we should get back z. That's what we think we want. Alright, so let's see how we proceed. We let, so this is a let, and we say that let the solution, or one of the root looks like a row. This is a row, p, okay, the Greek p looks like row, and theta. And we say that, hey, if this is one of the root, and when we exponentiating by n, then by De Mor's theorem, the row becomes row n because we are exponentiating by n. The cosine theta becomes, later on you'll realize the n goes in and becomes n theta, right? So this is the expression from the root exponentiating by n. So this is rho n cosine n theta plus I sine n theta. But hey, we know what z is. We know what z is. What's that? Z was r cosine phi plus I sine phi. So we can now identify the terms. R is rho n. Phi is n theta. Okay, and with that, since this is given to us, we now know how to find rho and theta. Okay, so this is given. So rho n is equals to r. Therefore, rho is equals to nth root of r. So r is a real number, so we can take the n root. It's a positive real number, right? Because it is a modulus. What about phi? Okay, phi is given to us because phi is from the original z. Now we have n theta equals to phi. So where is this k, 2k pi coming from? Remember that when we have phi and we have 2k pi plus 2 pi or 4 pi or 8 pi, it is the same z. Okay, let me explain. So if z is equals to r exponentiating j phi, isn't this the same as r e j phi plus 2 pi? Because nothing changed when we add 2 pi to this phi. Because if let's say this is r and this is phi, then what is phi plus 2 pi? This is phi plus 2 pi. We just add 2 pi to phi, we get back the same point of z. So z is equals to r e j phi is equals to r e j phi plus 2 pi. Or in fact equals to r e j phi plus 2k, where k is integer pi. Okay, so since now we get n theta equals to phi plus 2k pi, so theta is equals to phi plus 2k pi divided by n. So this is the expression that we want. And let's see the expression again. The expression is here. Let's erase this rubbish. And this is the expression that we want. Okay,